We want to find all prime numbers p such that 2p minus 1 and 2p plus 1 are also prime as well. Okay, let's just experiment. Let's start with the smallest prime number, p is 2. Well, that will work there. What will 2p minus 1 be? That would be 3. And then 2p plus 1, that would be 5. Okay, cool. So p equals 2 works. Let's try 3. What happens if we try 3? P is 3, cool. 2p minus 1 will be 5, cool. And 2p plus 1, that's 7. Those are all prime, great. P equals 3 works. If you try p equals 5, you get 2 times p minus 1 is 9. Uh-oh, that won't work. Even though 11 is prime, 9 is not. So that one doesn't work. Okay, and you could perhaps experiment some more, but how do we solve this? The key is to observe something about multiples of 3. We've got three numbers here, and we can assume now that p is bigger than 5 because we've already checked the first three cases. What can we say? Well, if p is bigger than 5, it's definitely not a multiple of 3. So this guy, not a multiple of 3. But if p is not a multiple of 3, then 2 times p can't be a multiple of 3. So the 2p, not a multiple of 3. But 2p is sandwiched in between 2p minus 1 and 2p plus 1. And since this is a string of three consecutive integers, one of them has to be a multiple of 3, and we've just said it's not 2p, because we're assuming, again, p is bigger than 5. So that means one of these guys here must be a multiple of 3, which maybe is going to be cause for concern because it's supposed to be prime. So what's the only multiple of 3 that's prime? It's 3. So let's deal with this case. If that guy is 3, you get 2p plus 1 is 3, which means p is 1, which not only is it not prime, it's also not bigger than 5. So that's useless. What about if this guy is 3? Well, then you get p equals 2, which is prime, and we've actually kind of already considered that here, but we were only assuming p is bigger than 5. So in fact, this just has two solutions, namely p is 2 and p is 3.